Extendable hashing. Hashing. In file structure, hashing is a technique used to quickly locate data within a file or database. It involves applying an hash function to the data and using resulting hash value as an index or a key to store and retrieve the data efficiently. Hashing allows for efficient storage and retrieval of data because it reduces the search space by using the hash values as an index. When the hash function distributes the data uniformly across the hash table, the average time complexity for insertion and retrieval operations can be closer to constant time of 1. However, collision can still occur, which may degrade the performance if not handled properly. Different types of hashing function and collision resolution strategies exist, and the choice depends on various factors such as nature of data, expected data, distribution and performance and requirements. Extendable hashing. Extendable hashing is in file structure used in computer science to organize and access the data efficiently. It is particularly useful for applications that require dynamic and efficient access to data and with a varying number of records. In extendable hashing, data is stored in hierarchical directory structure called as an extendable hashing table. The hash table consists of fixed number of buckets and each capable of holding a fixed number of records. Each bucket is identified by unique binary address, which is determined by applying a hash function to the records key. The key feature of extendable hashing is that the directory structure can dynamically grow or shrink as needed, depending on the number of records and the desired performance. This adaptability makes extendable hashing suitable for applications where the number of records may change frequently. Initially, the extendable hashing table starts with a single bucket and an empty directory. As records are inserted, the hash function is used to determine the bucket where the record should be placed in the bucket is full. The directory is expanded by adding one or more bits to the directory address. The expansion splits the overflowing bucket into the two new buckets and updates the directory to the points to the new buckets. The decisions of which the bucket to split is based on the least significant bits of the record's hash value. By adding one or more bit to the directory address, only half of the existing buckets need to be split, resulting in the minimum amount of data movement during the directory expansion. On the other hand, if the bucket becomes empty due to deletion, the directory can be shrunk by removing one or more bits from the directory address. The process merges adjacent buckets into single buckets and updates the directory according to the shrinking operation ensure that the directory does not become too large for the existing number of records, preventing unnecessary storage overhead. Extendable hashing provides the efficient search, insert, and delete operation with an average time of complexity of O of 1. The number of disk access required to perform these operations is typically small, making it suitable for the disk-based storage system. Extendable hashing example: there is directories and the buckets which is consist of data, local depth, global depth, etc. Advantages of hashing: minimal collision handling. Extensible hashing minimizes collision by using a multi-level directory structure. Each directory entry points to a bucket that holds a subset of keys. When a collision occurs, only the affected buckets need to be split, resulting in fewer collisions compared to the other collision resolution methods. This reduces the time spent on the collision handling and improves overall performance. Minimal collision handling. Extensible hashing minimizes collision by using a multi-level directory structure. Each directory entry points to a bucket that holds a subset of keys. When a collision occurs, only the affected buckets need to be split, resulting in fewer collisions compared to other collision resolution methods. This reduces the time spent on the collision handling and improves the overall performance. Balanced bucket distribution. Extendable hashing ensures a balanced distribution of key across the buckets. By utilizing the directory structures, keys are divided into multiple buckets and the splitting of buckets is performed intelligently to maintain a uniform distribution. This prevents hotspots and ensures that each bucket consists a manageable number of keys, optimizing search and retrieval time. Scalability. Extensible hashing offers excellent scalability. As the number of entries increases, the hash table can dynamically grow by splitting buckets and extending the direct structure. This ability to scale without require a complete restructuring of hash table makes extensible hashing suitable for applications that need to handle a varying number of entries over time. Extendable hashing. Lower space overhead. This space overhead of extendable hashing is related to low compared to other hashing techniques. The directory structures requires additional memory to store the pointers to the bucket, but it grows at a slower rate compared to the number of entries. This makes extensible hashing memory efficient, especially when dealing with the large data sets. Conclusion. Overall, extendable hashing offers a balance between storage efficiency and access performance, making it popular choice for application and that require dynamic data management with fast access time. Thank you.